Thank you very much. This is Saiful Amin from Bangladesh University of Engineering and Technology. And the beauty of this SATREPS project is a very deep collaboration between Japan and Bangladesh, not only between only the two universities, one in Japan and one in Bangladesh, but with several universities in Japan, several leading universities in Japan, with several leading universities in Bangladesh. And another beauty of this project is that we are working with the professional engineers, both in Japan and also in Bangladesh. That's why our Public Works Department and Housing and Building Research Institute, the major stakeholder for official research for building in Bangladesh, is leading the whole project. And in Bangladesh, our major building stocks are at this moment that we are concerned are basically of reinforced concrete. That's why our research is basically concentrated on reinforced concrete structures. And so here the basic terminology comes for the two materials. One is concrete and another one is steel, but as a reinforcement. And as we know, in Bangladesh, there is a lot of undocumented construction history. So in that way, we actually don't know the strengths of our buildings, basically the concrete strength in most of our buildings. But for any assessment, we need to have a judgment. We need to have a realistic and specific judgment for the concrete strength, at least for the screening purpose. And we cannot forget the threat of earthquake that that can happen anytime in Bangladesh because of the proximity of our neighboring countries having the fault lines, and we also have some published literature about the location of some fault lines even within Bangladesh. And we are also having some medium earthquakes with epicenters in Bangladesh in the recent past. So in that way, we do have the threat from earthquake. But another alarming news is that the Rana Plaza collapse or Sabah Spectrum Garments collapse that occurred in Bangladesh are the total whole building collapse, leading to loss of life and property, but that fall under the gravity load. So what went wrong on those structures? Basically, the concrete strength was the factor that was blamed for. So when we want to go for screening the building for detailed assessment, we need to be realistic and we need to be safe from our side so that we can evaluate a large building stock rapidly. That's why in the morning you already have presentations about the rapid visual scanning, and where our researchers and colleagues from Public Works Department and Tohoku University already mentioned that we can evaluate the building stocks very judiciously if we follow some methods. But the major ingredients for such a thing is that the concrete strength that we need to estimate. So having the practical scenario in Bangladesh where we don't have any record or we have very little record about the authentic information about the concrete strength of the building that we are targeting to investigate. And we also have shallow column dimensions that restrict us to take cores from all those columns because it is very risky. So we take the resort to non-destructive testing technology, and which can be used to identify the weak buildings, or at least to screen out the bad buildings from the good buildings. That is the objective of this chapter. It is chapter 2, So it is actually the beginning of the chapter of the manual. But of course, because of my busy schedule in the morning, I had to take the time at the last part of this session to present it. And this project, the SWIP project, funded by SATREPS and JST, is a result of a CNCRP project, and that made some in-depth fundamental survey of the buildings. And this was also presented in the morning by Masukawa Sensei from University of Tokyo, and our other colleagues also in Japan included this in our earlier presentations of today. And where we see that we have a large number of building stocks that does have strength below 10 MPa. So below 10 MPa put us to the basic focus to investigate the structural performance of our major building members, be it a flat plate or be it a beam column joint or be it a column ductility issue. We focused on the low strength concrete. And so we had two border lines in a broad sense, 10 MPa and 20 MPa. So in that way, we define some of the methods, and we propose some of the methods to use simultaneously, because a non-destructive test will give us some assessment value. So one method is not always so good. That's why we are using two methods together simultaneously. That is here our proposal. And finally, we this leads to the classification of concrete, and that will be presenting at the end of this presentation. So the basic procedure, we always, most of us and maybe everyone knows about the rebound hammer. But here we have proposed a rebound hammer of a little bit different specification, which we call, which depend on the velocity ratio. Actually, velocity ratio gives us some benefit apart from our traditional normal original Smith hammer, which we call the original rebound hammer, and because it is direction independent. So because it depends on the velocity ratio, as you see in the first part of this presentation. And here at the tip, it has a flattened edge. We call it mushroom type of hammer or mushroom head. So mushroom head gives us a wider area for judgment. So otherwise, we might have some biasness. We have seen in our result the biasness when we use the normal head hammer. Normal head hammer has a smaller area, but here mushroom head gives us a larger area. And it's not a new device we propose here. It is actually commercially available from many manufacturers. Renowned manufacturers. So we choose this device. And another device we choose here is the scratching testing device. It is basically based on the groove width. We apply a specific force through spring and indent the concrete and measure the groove width. So these two basic procedure will be applied on a prepared surface of concrete, because we need to remove the plaster and other debris, and we need to grind the surface by hand grinder in a smooth way. And all these things are presented in our manual. So with all the basic test, we'll after the plaster removal, we'll apply the rebound hammer and the scratching test, and we'll select the lower compressive strength. And based on this, we'll classify the concrete. And if we can also go to other things. If the concrete strength and the construction time is available, then the target structure is well maintained, and we'll have the concrete strength. So we can take the other any of the two routes. So this is the basic policy to characterize the concrete strength. One thing is we need to have the concrete strength. We want to have the concrete strength from the basic data that was gathered during the construction phase or some test data. So here we are presenting the concrete classes. We broadly divided the concrete into the two parts. One is after 2006. Another period is between 1993 to 2006, and another one is before 1993. So we call it old buildings, middle range buildings, and new buildings. And in our study that we came from the CNCRP project, we replotted this figure here, and here you will see the bottom mark is around 5 MPa or around 10 MPa. So we took the conservative value. If nothing is available and it is an old building, we propose for 5 MPa to start with the old buildings. And between 1993 and 2006, we take about 9 MPa, and after 96, we can take it more than 9 MPa. So this is our initial assumption. Of course, it is from the safe point of view. Then the thing is that what if we can find something better in our test? So major range of classifications will go for the based on test that I'll be presenting in the next slide. So here it is found that from our laboratory and field test that rebound number, if the rebound quotient Q value, actually in our original Smith hammer, we say that R value, but here we'll go for Q. That means the mushroom head velocity ratio value. If it is very low, less than 30, we call it, we have to say that it is a very low strength, and it will be less than 9 MPa strength. And if it is between 30 to 35, then the strength range will be indicative of like this. And if it is between 30 to 40 Q, then it is indicative of like this. And then if it is more than 40, then it's a good concrete. That means it has a characteristic strength greater than 21 MPa. So from our result, we have seen the standard deviation, and the standard deviation is quite interesting. You can see here standard deviation for the higher the strength, higher also the standard deviation. That naturally means that the low strength concretes are confidently really weak, but high strength concretes there is a scatter. There is a scatter that we have found in our rebound hammer test result in our laboratory and also in the field test. And if we go for the classification for compressive strength, if we look at it based on the scratch width, we can see if scratch width is less than 1 millimeter, greater than 1 millimeter, or groove width is greater than 1 millimeter, then it can be 9 MPa and less. But if the groove width is 0.5 to 1 millimeter, then it is a second range, and it is third range and fourth range. So there is a good correlation between the two methods. First method is based on the Q value, and the second one is based on the groove width. Groove width means the indentation width that we can measure from this scratching device, and we can measure the indentation width here, and from here we can go for the scratching test. So how we do it? Basically, this table has prepared based on evidences, and the evidences that we gathered in Bangladesh in our laboratories, and also in the field condition in Bangladesh, and also in a laboratory in Tohoku University. And here we have in our team basically Professor Nishiwaki and myself in Buet, and also the big SATREPS team. We all work together. And Miss Maisha Maliha, who is now in Tokyo University, did his graduation and post-graduation thesis in Tohoku University under the, with this topic. So based on this, we could come out these results that we are presenting here to you today. If we look at the evidences, and we can see there is a direct correlation between the rebound coefficient and the groove width. And if the rebound coefficient increases, basically the groove width decreases because it is a stronger concrete. But if the rebound coefficient decreases and groove width increases, basically groove width has to increase for the low strength concrete, and we can see this part, and it is basically a very low grade concrete. But this is some part which is basically we want, or we think, because it is 21 MPa or more strength. So this is our minimum expectation, that our buildings are having above 21 MPa. That is the major part. Then if it is or we will have something here, or we will have something here, or unfortunately if we have something less than 9 MPa, then we cannot move forward. Yes, and here we gave you the good correlation we achieved for the groove width and the compressive strength, and here we see there is a inverse relation, and higher the groove width, lower the compressive strength. And here we determine the groove width for different specimens. These are the field conditions in Bangladesh, and also there are the Japan laboratory conditions, and so on. And we find out this type of correlation. And for the rebound coefficient, basically, if we look at the ProSec calibration, it is a little bit away. ProSec hammer we used in our study, but of course we find out our own correlation for the rebound coefficient Q and the compressive strength, and as you see in the relation. And definitely we perform the statistical analysis for each of the strength ranges here, here, and here. And what the statistical analysis says here, this is basically, this statistical analysis are based on the 3 ranges. If we look at the range Q is less than 30, or groove width is less than 1, we can see such type of distribution where the probability of occurrence is about 100%. Yes, but if we go to the higher strength, for example, if we want to declare some concrete of above 21 MPa, we can see the probability is around 7 normal distribution function. It is around 72% or 75%, and in between we have the other values. But of course, this gives us the good confidence that our ranges are coming where. So it is about 9 MPa or below the one range, and this range is coming from here to here, 9 to 13, and here is 14 to 21, and this one is 21 and above. So based on this, we are giving such a classification, and this is the philosophical figure where we take the Q value and groove width value as an NDT value as a parameter, and we correlated it with the cylinder compressive strength with a calibration function and statistical analysis. That's all from me today. And if you have any question, you can ask us. Our research team is here, and they will take all of your suggestions very correctly and accurately, so that we can get benefit of from your comments in our project. Thank you very much.